Good day to all of you. So we're already on chapter 18 of the operating systems lecture, which is all about virtual machines. So before we start our lesson, so virtual machines, it is a very innovative technology. Why? Because of this technology, we can use another operating systems aside from the operating systems that we are using. You do not need an extra computer for you to install that operating systems that you want to explore or to use also. So it is different with the dual booting, because with dual booting, yes, you can have as many operating system as you have, but the disadvantage of using the dual boot is that you cannot use two or more operating systems at the same time as long as your computer system permits. So for dual boot, for example, you have Windows and Linux, any flavors of Linux. Then if you want to use Windows, of course, you're going to select the Windows to boot by means of the grab bootloader. And then, for example, you're already in Windows and you want to use the Linux operating system, any flavors of it. So you need to restart, and then it will again boot from the grab bootloader. And of course, you're going to select the Linux flavor that you want to boot. So that's the disadvantage of using dual boot. But of course, its advantage is the resources such as the CPU, the memory, will be solely dedicated to that operating system. While for virtual machines, you can use two or more operating systems all at the same time. But then again, if your computer system permits, and then it's like the host operating system will act as an application software inside the host operating system. So to understand more and to know the technical details of about virtual machines, so let's start our lesson. So again, chapter 18 is all about virtual machine. It is one of the advanced topics of operating systems. So the contents of chapter 18 are, we have the overview, so the history of virtual machines, the benefits and features of virtual machines. I've mentioned some of these benefits and features. And then we have this building blocks, and then types of virtual machines and their implementations, virtualization and operating system components, and last but not the least is we have examples. So the chapter objectives for this virtual machines are, first is explore the history and benefits of virtual machines, discuss the various virtual machine technologies, describe the methods used to implement virtualization, show the most common hardware features that support virtualization, and explain how they are used by operating system modules, and discuss current virtualization research areas. So for the overview of the virtual machines, so the fundamental idea here is that abstract hardware of a single computer into several different execution environments. So that is the fundamental idea. So I've already mentioned that you have the host operating system, and you can have as many as guest operating systems as long as your computer system allows it. So it is similar to layered approach, but that layer creates a virtual system, which is a virtual machine, or in short VM, on which operating systems or applications can run. So there are several components. First is we have the host, or the underlying hardware system. So for the host, for example, is your laptop or your desktop computer where your operating system will be installed. And then we have the virtual machine manager, or the VMM, or hypervisor. That's the other term for virtual machine manager. So this creates and runs virtual machines by providing interface that is identical to the host. So virtual machine manager is actually a software. So examples of virtual machine manager. So I am most familiar with Oracle VirtualBox. And then there is the VMware player. But I do think there are other virtual machine managers that exist, but these two are the most popular. So we have there, except in the case of paravirtualization. So actually, this will be discussed later. But for you to understand what is paravirtualization is, it is a technique in which a guest OS is modified to work in cooperation with a virtual machine manager. And then the last component of a virtual machine is the guest, the process provided with virtual copy of the host. So it is usually an operating system. So that's why I'm having the term guest operating system, and then we have the host operating system. And then single physical machine can run multiple operating systems concurrently, each in its own virtual machine. So I can say, as I've said, that if you have an operating system that is installed, which is the host operating system, you can have multiple operating systems running concurrently. But then again, as I've said, it depends upon the capacity of your computer system, because the guest operating system can use a portion of your CPU and your memory. So if your computer is a high end that has a very big memory and your CPU has many cores, then you can expect that you can run multiple operating systems concurrently. Again, it depends upon the system, but it's possible to run multiple operating systems concurrently or simultaneously, aside from your host operating system. So we have the system model here. So for a non-virtual machine, so as this one that we're using typically, so we have the hardware, then we have the kernel, and then the processes. While for a virtual machine, so we have the hardware, and we have the virtual machine manager, for example, Oracle VirtualBox. And then you can create as many of virtual machines that you can, for example, you want Linux, Mac OS, and then a lower version of Windows. You can do that. But running them concurrently depends upon the capacity of your computer system. But of course, if you're going to have a virtual machine for every computer, you have to be reminded that they, of course, occupy space. At least they occupy the minimum system requirements for their hard drive. Okay, so that's why if you have three virtual machines inside your system, and then for example, it's minimum requirement for the capacity of the hard drive is, for example, 10 gig. So if you have three, so it will already occupy 30 gigabyte space. It's like just a typical application program that also occupies space. And then, of course, if you're going to run your virtual machine, they will have their own kernel. And then, of course, they have their own sets of processes. So implementations of virtual machine managers. So it varies greatly with options including. So we have actually three types of hypervisors or virtual machine managers. So we have the first, we have type 0. It is hardware-based solutions that provide support for virtual machine creation and management via firmware. So examples of Type 0 hypervisors are IBM LPARs and Oracle LDOMs. So IBM LPAR, so LPAR means logical partition, while LDOM is logical domain. So in other words, this Type 0 hypervisors are inside the hardware. You're not going to install it, is already set up in a hardware, in your computer system, to be exact. Okay, next is we have type 1 hypervisors. These are operating system-like software built to provide virtualization. So examples of this is we have the VMware ESX. So it's another virtual machine manager, of course. So ESX means Elasticity SkyX. We have Giant Smart OS, and then the Citrix Zen server. Okay, another variation of type 1 hypervisors. So this can be general purpose operating systems that provide standard functions as well as virtual machine functions. So examples of these hypervisors are the Microsoft Windows Server with Hyper-V or Hyper-Virtualization, and Red Hat Linux with KVM. So KVM stands for kernel-based virtual machine. So it's like type 1 hypervisors has two variations. And last but not the least, we have the type 2 hypervisors. So these are applications that run on standard operating systems but provide VMM features to guest operating systems. So categorized from with type 2 hypervisors are VMware Workstation, so the VMware Player and Fusion, Parallels Desktop, and Oracle VirtualBox. So again, I'm familiar with the Oracle VirtualBox because I've used it so many times. Okay, next, aside from this type 0 to type 2 hypervisors, we have other variations, which includes Paravirtualization. So it is a technique in which the guest operating system is modified to work in cooperation with the virtual machine manager to optimize performance. Then another variation is we have the programming environment virtualization. So VMMs do not virtualize real hardware but instead create an optimized virtual system. So this is used by Oracle Java and Microsoft.NET. And then another variation is we have the emulators. So allow applications written for one hardware environment to run on a very different hardware environment, such as a different type of CPU. As you can remember, emulator, I've already um, illustrated, shown you how emulator works in our previous lessons. So for example, if you have a game, a software, for example, a PSP game, of course, PSP game runs natively with PlayStation Portable, of course, PSP. And then you need a PSP emulator for you to use that game software. So actually, because maybe of the people who love games, they created emulators so that instead of buying the hardware, and maybe they don't have money, maybe that's the case. So if they want to still enjoy the games that is for example that they like, that they don't have the console, at least they can play it in the PC by using an emulator. Actually, there are many emulators exist. There is for I saw another from an emulator for DS, an emulator for Nintendo 64. There's also an emulator for arcade games that you can find in, for example, arcade games in the malls. So there are a lot of emulators. And then we have also the application containment. So not virtualization at all, but rather provides virtualization-like features by segregating applications from the operating system, making them more secure and manageable. So examples of this are Oracle Solaris zones. We have BSD jails and IBM AIX WPARs. So again, AIX, I've already mentioned it in our previous lesson. AIX means Advanced Interactive Executive, and WPAR is Workload Partition. So the variation, so much variation due to breadth, depth, and importance of virtualization in modern computing. So the history of virtual machines. So it first appeared in IBM mainframes in 1972, but of course, mainframes are mainly used for, it's not for consumer use. So that's why at that time, people are really not aware that virtual machines already exist. So it allowed multiple users to share a batch-oriented system, and then formal definition of virtualization helped move it beyond IBM. So a VMM provides an environment for programs that is essentially identical to the original machine. Programs running within that environment show only minor performance decreases. And then the VMM is in complete control of system resources. So in the late 1990s, Intel CPUs are fast enough for researchers to try virtualizing on general purpose PCs. So Sen, of course, a company, and VMware created technologies which are still used today. And then virtualization has expanded to many OSs, CPUs, and virtual machine managers. So, what are the benefits and features when you're going to, if you're going to use a virtual machine or a virtual machine manager? So the host system protected from the virtual machine and virtual machines protected from each other. So what is the advantage? There's exclusivity for if this virtual machine runs, it will not affect the host and it will also not affect the other virtual machines. So the advantage of this is that the effect is a virus less likely to spread. For example, your host operating system is Windows and then you're using a lower version of Windows. For example, Windows 10 is your host operating system. Your guest operating system, for example, is Windows 7. And of course, carelessness. There is your system in Windows 7 is affected by the virus which is running in a virtual machine manager. It will not the virus will not spread in to the host system because it is separate. It's like the term sandboxed. So if the virus will spread, it's only to that virtual machine. And then sharing is provided through via shared file system volume network communication. So I'm talking about the VirtualBox. They have this feature that if you want to access the a drive or a folder inside that virtual manager, there is a setting that you need to set up so that that particular folder, if you're inside that virtual machine, you can still access the files. Okay, another benefits and features is that you can freeze. You can freeze the operating system or the virtual machine while it is running in the host system. You can also suspend. For example, it's like freeze. The only difference with suspend is you're going to turn off the virtual machine manager, and then, for example, you're going to restart or you're going to log out, and then you're traveling, for example, and if you want to continue to use the operating system, and then you're going to open the virtual machine manager, and then you can see that the operating system that you are using that virtual machine is suspended, then you can resume your operations of that virtual machine. And of course, you can run a virtual machine because that's the purpose of the virtual machine manager. So then can move or copy somewhere else and resume, snapshot of a given state, able to restore back to that state. So it also has the capability to save the snapshot of the system. So some VMMs allow multiple snapshots per virtual machine. So another characteristics is we have clone by creating copy and running both original and the copy virtual machine. So because of these possibilities and innovations in virtual machines, these are great for OS research, better system development efficiency, and then of course, VMMs can run multiple different OSs on a single machine, as I've already said. And then there is consolidation, application development. You can do that in the other virtual machines. So consolidation, so the practice of running multiple guests per host, reducing the number of physical servers needed for a given workload. So that's what I'm saying from the start of this lesson is that you don't need another set of computers for you to try or to use another operating system with a different architecture from your host. Okay, continuation for the benefits and features. So another benefits is we have the templating, create an OS plus the application VM, provide it to customers, use it to create multiple instances of that combination. And then we also have this live migration, move a running VM from one host to another. So from the word itself, so the system is running and you can move it from one host to another. And because of live migration, there is no interruption of user access. And then all these features taken together is we have the cloud computing. So cloud computing means that you do not need a computer or a laptop for you to do things. As long as you're online and your data and information, the needed files is already online, you can do it anywhere and of course anytime, even without um, a traditional computer. So that's why there are services, for example, Google Docs. So for Google Docs, you can already edit your files by using Google Docs. You don't need to install Office Productivity Suite for you to edit files, documents to be exact. So as long as you have an internet connection, you can edit documents, slideshow presentations, and spreadsheets in Google Docs. So that's an example of cloud computing. And there are also other applications that are already migrating from installing it from the computer, and then you have to just access their portal to avail of the services provided by these software companies by means of cloud computing. Okay, next is we have the building blocks. So generally difficult to provide an exact duplicate of underlying machine, especially if only dual mode operations available on CPU. So the dual mode is the user mode and kernel mode, if you can remember. But getting easier over time as CPU features and support for VMM improves, of course, because of technology, advancements in technology. And most VMMs implement the virtual CPU or the vCPU to represent state of CPU per guest as guest believes it to be. And then when guest context switch onto CPU by VMM, information from vCPU loaded and stored. And then there are several techniques as described in next slides. So for the first building block of virtual machine is we have the trap and emulate. So dual mode CPU means guest executes in user mode. Actually, guest operating system executes in user mode because guest OS is considered, it's just like a normal application program. So the kernel runs in kernel mode. Not safe to let guest kernel run in kernel mode too. So what happens is that, so the virtual machine needs two modes, virtual user mode and virtual kernel mode. So both of which run in the real, of course, because VM is a virtual machine. So they have this also has two modes, the virtual user mode and the virtual kernel mode, but in reality, the VM runs in real user mode of the host operating system. So actions in guest that usually cause a switch to kernel mode must cause a switch to virtual kernel mode. So continuation with the trap and emulate. So how does a switch from virtual user mode to virtual kernel mode occur? So these are the steps. So attempting a privileged instruction in user mode causes an error which is called a trap. And then the VMM gains control, analyzes the error, executes operations as attempted by the guest, and then returns control to guest in user mode. So that is the term trap and emulate. So most virtualization products use this at least in part. And then the user mode code in guest runs at same speed as if not a guest. And then but kernel mode privilege mode code runs slower due to the trap and emulate. So it is especially a problem when multiple guests are running, each needing trap and emulate. So for your computer system, even though it can handle multiple OSs or guest operating systems at the same time, but of course, if you really are serious with your operating system, as much as possible, just run one virtual machine at a time. And then CPUs adding hardware support, made CPU modes to improve virtualization performance. So this is an illustration of the trap and emulate virtualization implementation. So we have here, we have the guest operating system, which runs in the user mode. And then we have our virtual machine manager, which runs in the kernel mode of the host operating system. So for example, the guest operating system, of course, it has its own user processes. And then there is a privilege instructions that wants to use the kernel. So it will send a trap, and then the VMM will emulate the action, and then it will update the virtual CPU, and then it will return. It depends upon the request of the privilege instruction. So next building block is we have the binary translation. So some CPUs don't have clean separation between privileged and non-privileged instructions. So earlier Intel x86 CPUs are among them. Of course, there are relatively old systems. So the earliest Intel CPU designed for a calculator. Of course, there is a possibility that our calculators now is using the very old versions, the Jurassic versions of Intel CPUs. And then backward compatibility means difficult to improve. So backward compatibility means, for example, if you have a computer system that can run in Windows 10, it should also can handle older systems such as Windows 7, Windows ME, or Windows 98 if it's still available. So that's the meaning of backward compatibility. And then consider the Intel x86 POP-F instruction. POP-F means pop flag. So this pop flag instruction loads CPU flags register from contents of the stack. So if CPU is in privileged mode, all flags are replaced. And if CPU is in user mode, then on some flags are replaced. And then no trap is generated for this example. Okay, let's continue our discussion with binary translation. So other similar problem instructions we will call special instructions. So this cause trap and emulate method considered impossible until 1998. Then of course binary translation solves the problem. So basics are simple, but implementation is very complex. So such as if guest vCPU is in user mode, guest can run instructions natively. And on the other hand, if guest vCPU is in kernel mode, guest believes it is in kernel mode. So the VMM examines every instruction guest it is about to execute by reading a few instructions ahead of program counter. Then non-special instructions run natively, and special instructions translated into new set of instructions that perform equivalent tasks, for example, changing the flags in the vCPU. So continuation implemented by translation of code within the VMM. And then the code reads native instructions dynamically from guest on demand, generates native binary code that executes in place of original code. And then performance of this method would be poor without optimizations. So products like VMware uses caching. So how does VMware do this? This caching translate once, and when guest executes code containing special instructions, cache translations used instead of translating again. Testing showed booting Windows XP as guest cost 950,000 translations and a 3 microseconds each, or 3 second, a 5% slowdown over native. So we have this illustration of binary translation virtualization implementation. So we have, again, the guest is running in user mode, the guest operating system, and then our virtual machine manager runs in kernel mode. And then, of course, it already also has a set of user processes, and then the VMM reads instructions. If there is a special instruction, then it will send to the virtual machine manager, and then it will be translated, and then the vCPU will be updated, and it will return to the guest operating system whatever the request of the special instruction. So next is we have the nested page tables. So memory management, another general challenge to VMM implementations. So how can VMM keep page table state for both guests believing they control the page tables and VMM that does control the tables? So to answer that, so the common method for trap and emulate and binary translation is nested page tables, or NPTs. So for this one, each guest maintains page tables to translate virtual to physical addresses, and then the VMM maintains per guest NPTs to represent guest's page table state, just as vCPU stores guest CPU state. And then when the guest on CPU, then the VMM makes the guest's NPTs the active system page tables. And then the guest tries to change the page table. So the VMM makes equivalent change to NPTs and its own page tables. So the only problem with nested page table is that can cause many more TLB misses or the translation look aside buffer. So it will entail much slower performance. So another building blocks is the hardware assistance. So all virtualization needs some hardware support. So more support, more feature-rich, stable, better performance of guest operating systems. So for Intel, they added the VTX, so the virtualization technology for Intel. So these are the VTX instructions in 2005, and AMD, the AMD-V, virtualization instructions in 2006. So you can conclude that from 2004 and earlier years, computers do not support virtualization. So you cannot you can install VirtualBox or any other virtual machine managers, but it will be very difficult for you to install a virtual machine or I guess operating system because the actual um, central processing unit or CPU does not support virtualization. So this Intel VTX and AMD-V instructions, so CPUs with these instructions removed a need for binary translation, generally define more CPU modes, the guest and the host. VMM can enable the host mode, define characteristics of each guest virtual machine, switch to guest mode and guests on CPUs. And in guest mode, guest OS thinks it is running natively. It sees devices as defined by the VMM for that guest. And then, of course, access to virtualized device, privilege instruction, cost drop to VMM, and then the CPU maintains the vCPU context switches it as needed. So hardware support for nested page tables, DMA interrupts as well over time. So of course, because of the advancement of technologies. So this is an illustration of a page table. So this shows extra translation work performed by the hardware to translate from a guest virtual address to a final physical address. So we have here, so why it is very taxing for the hardware because from the guest OS, and then it will really translate the addresses to the physical address. So we have this one, so the guest virtual address and then the kernel paging data structures, and then we have the guest physical address. It is composed of PML4 directory pointer, the directory table, and the offset. So for number one, the PML4, so PML stands for page map layout. So then we have this PML for E. So we have level 4, then E is for entry. So this will be translated to, it will be equivalent here because it's a broken line. This will be, of course, the allocation for the host physical address, but this is for number one. And then the directory pointer is we have the PDPTE. So that stands for page directory pointer table entry. And then we have the directory, the page directory entry. And then we have the PTE, the page table entry. And then for the offset, we have the physical address. And then this will be combined here. As you can see, the L4E will be situated here, and then this will be used by the PDPTE, and then after that, adding the PDPTE, it will be used by the PDE, and then this PDE is a combination already of PML4E, PDPTE, and PDE. And then this PDE will be used by PTE, and then it will add the page table entry, and then you're going to store it in the host physical address, and then plus the physical address itself, and then number 5, we have the offset. So it will complete the physical address. So it's very taxing if we're going to use nested page tables for the host guest operating system. Okay, next is we have the types of virtual machines and implementations. So many variations as well as hardware details. Assume VMMs take advantage of hardware features, and then these hardware features can simplify implementation and improve performance. Whatever the type, a virtual machine has a life cycle. So the first is created by the virtual machine manager. And then next is resources are assigned to it, can be a number of cores, amount of memory, networking details, and storage details. So for type 0 hypervisors, resources are usually dedicated because the virtual machine manager is already inside the hardware or the firmware. And then other types dedicate or share resources or a mix. And then when no longer needed, the virtual machine, the VM can be deleted, freeing resources. So steps are simpler, faster than with a physical machine install, and then can lead to virtual machine sprawl with lots of VMs, history, and state, which is difficult to track. So again, virtual machine sprawl. So the situation in which there are so many VMs on a system that their use and history and state become confusing and difficult to track, it is caused by the ease of creating virtual machines. Because of course, advanced technologies such as the Intel's VTX and AMD V, and of course, it really becomes easier to install virtual machines. You don't need to fear what will happen if you have wrong installation, because it makes the installing of virtual machines very easy because of this VMMs. Okay, so we already have an overview of the types of hypervisors, but this slides we're going to discuss specifically or in detail the types of hypervisor. So let's start with type 0. So the type 0 hypervisor, it is an old idea under many names by hardware manufacturers. This can be, the names are partitions or domains, and it is also hardware feature implemented by firmware. So OS need to do nothing special, and then VMM is already in the firmware. So smaller feature set than other types, and then each guest has a dedicated hardware. So IO is a challenge as difficult to have enough devices, controllers to dedicate to each guest. And then sometimes VMM implements a control partition. So this control partitions runs daemons that other guests communicate with for shared IO. And then type 0 hypervisor can provide virtualization within virtualization. Guest itself can be a VMM with guests. So other types have difficulty doing this. So type 0 hypervisor. So this is an illustration of a type 0 hypervisor. So again, the virtual machine manager is already inside the firmware. And then it is up to the hypervisor to allocate the CPUs and memory to the guest. And then there's a possibility that a guest operating system can be a host also to other guests. So that is the type 0 hypervisor. Okay, next is we have the type 1 hypervisor. So commonly found in company data centers, in a sense becoming data center operating systems. Then data center managers control and manage OSs in new, sophisticated ways by controlling the type 1 hypervisor. Consolidation of multiple OSs and applications onto less hardware, and then move guests between systems to balance performance. And then this has the capability of snapshots and cloning. So special purpose operating systems that run natively on hardware. That is another variation for type 1 visors. Aside from company data centers, there are also special purpose operating systems. Rather than providing system call interface, create, run, and manage guest OSs, can run on type 0 hypervisors but not on other type 1s. And it runs in kernel mode. The guests generally don't know they are running in a virtual machine. Implement device drivers for host hardware because no other component can. and also provide other traditional OS services like CPU and memory management. So another variation is a general purpose OS that also provides the VMM functionality. Examples of this are the Red Hat Enterprise Linux with KVM, Windows with Hyper-V, and Oracle Solaris. And also perform normal duties as well as VMM duties, typically less feature-rich than dedicated Type 1 hypervisors. So in many ways, treat guests OSs as just another process, albeit with special handling when guest tries to execute special instructions. So that is for Type 1 hypervisor. Next is we have the Type 2 hypervisor. So as I've already discussed, Type 2 hypervisor, Oracle VirtualBox is an example, VMware Player. So less interesting from an OS perspective. So very little OS involvement in virtualization. And also VMM is simply another process run and managed by the host, which is the operating system. Even the host doesn't know there are VMM running the guests. So tend to have poorer overall performance because can take advantage of some hardware features, but also a benefit because require no changes to host OS. So that's why Type 2 hypervisors is easier to install. So students could have Type 2 hypervisor on native host, run multiple guests, all on standard host OS such as Windows, Linux, and Mac OS. Okay, another type is we have this paravirtualization. So it does not feed the definition of virtualization. The VMM not presenting an exact duplication of underlying hardware, but paravirtualization is still useful. So the VMM provides services that guests must be modified to use. Because of this leads to increased performance and less needed as hardware support for VMs grows. So Sen, leader in para-virtualized space, adds several techniques. For example, clean and simple device abstractions. The advantage will be efficient I/O, good communication between the guest and VMM about device I/O, and each device has circular buffer shared by guests and VMM via shared memory. So we have an illustration here of send I/O via shared circular buffer. So we have here the legend, we have the request queue, the outstanding descriptors, the response queue, and unused descriptors. So for this one, for this the darkest blue here, these are the outstanding descriptors. So descriptors slots awaiting a response from send. So this is an example, request consumer, private pointer in Zen. So it means it is already in the system. These are requests. And then the less darker, we have this one. Okay. Which of them is darker? Okay. The less darker is we have the here, the response queue, descriptors returned by send in response to service request. So this is the pointer for the response producers. So shared pointer updated by send. And then we have this one, the lighter color, blue. So the lighter one is the request queue. Descriptors queued by the VM but not yet accepted by send. So that's why the request producer, this is the pointer, this is the shared pointer updated by the guest OS. So it's not yet inside the send system. And then last but not the least, so this is the least dark of all the four. So we have this unused descriptors. So these are private pointers in guest OS. So this is the shared circular buffer that is used by Zen IO. So continuation for para-virtualization. So Zen, again, a leader in para-virtualized space, adds several techniques aside from what is mentioned in the previous slide. We have memory management does not include nested page tables. Each guest has own read-only tables. Then guests uses the hypercall or call to hypervisor, or again the VMM or the virtual machine manager, when table changes needed. And then Paravirtualization allowed virtualization of older x86 CPUs and others without binary translation. Guest had to be modified to use run on para-virtualized VMM, but on modern CPU, Zen no longer requires guest modification. And of course, there is no longer para-virtualization. So another type of VM is the programming environment virtualization. So also, not really virtualization, but using same techniques, providing similar features. So programming language is designed to run with custom-built virtualized environment. So for example, Oracle Java has many features that depend on running in the Java virtual machine or the JVM. So this is of course a virtual machine for Java. So in this case, virtualization is defined as providing APIs that define a set of features made available to a language and programs written in that language to provide an improved execution environment. So for JVM, compiled to run on many systems, including some smartphones even, and then programs written in Java run in the JVM no matter the underlying system. So actually, by using Java Virtual Machine, it is relatively more portable than others from other virtual machines. So it actually similar to interpreted languages. So interpreted languages is unlike compiling that you have to convert it into a native code. For interpreted language, you can run a program even it's in a high level programming language format. So that's the difference between compiled and interpreted. And another advantage of interpreted language is that you can already run the program even if you have not yet finished the whole code, just to see the effects of that particular line of command or in the source code. So another types of VM is we have the emulation. So there is a older way actually for running one operating system on a different operating system. So for virtualization, requires underlying CPU to be same as guest as was compiled for. So that is the characteristic of virtualization. While emulation allows guests to run on different CPU. As I've said, for example, if you have a PlayStation Portable, it uses a set of course, the central processing unit is for PlayStation Portable and its memory. But then you can run these games if you're going to install an emulator. It's like masking the the CPU memory of the computer as if that the game will not detect that it's a different hardware platform. So necessary to translate all guest instructions from guest CPU to native CPU. So it's emulation, not virtualization. Because again, virtualization is the characteristic in which the host and the guest OS are using just the same CPU and hardware. Then useful when host system has one architecture, guest compiled for other architecture. Then company replacing outdated servers with new servers containing different CPU architecture but still want to run old applications. So that's why you can still use, there's a still application for emulation. So what is the performance challenge? The order of magnitude slower than the native code. And then new machines are faster than older machines, so can reduce slowdowns. So that's the advantage because again of the advancement of technologies, the computers that were produced by this year or by this time, it's much faster than the computers that was invented in the 1970s or 1960s. And then emulation is very popular, so especially in gaming. So that's why that's the only thing that I can think of emulation because of course I also love games. Then I have this software version of this game so that I can play it anywhere in the computer without buying the console. Where old consoles emulated on new. So that's the purpose. If you do have a game and then your console is already damaged or you really don't have the console, then you can use emulator for you to play your old favorite games. Okay, another type of VM is the application containment. So some goals of virtualization are segregation of apps, performance and resource management, easy start, stop, move, and management of them. Can do those things without full-fledged virtualization. If applications compiled for the host operating system, then it don't need to be full virtualization to meet these goals. So for Oracle containers or zones, for example, create virtual layer between OS and apps. So only one kernel is running, which is the host OS. OS and devices are virtualized, providing resources within zone with impression that there are only processes on system. Each zone has its own applications, networking stack, addresses and ports, user accounts, and others. And then CPU and memory resources divided between zones. Zones can have its own scheduler to use those resources. So for Solaris 10, this is only an illustration in which it has two zones. So from the virtual platform device management, these two zones, but they have the same sets, such as user programs, system programs, network addresses, device access, CPU resources, and memory resources. And then, of course, we have the global zone. And this is how Solaris 10 illustrates or do with if they have these zones. Okay, next is we have virtualization and operating system components. Now look at operating system aspects of virtualization. So CPU scheduling, memory management, I/O storage, and unique VM migration feature. So how do VMMs schedule CPU use when guests believe they have dedicated CPUs? And another question, how can memory management work when many guests require large amounts of memory? So these questions will be answered on the later slides. So first is the CPU scheduling as for the question. So even single CPU systems act like multiprocessor ones when virtualized. And then one or more virtual CPUs per guest. And then generally, VMM has one more physical CPUs and number of threads to run on them. Guest configured with certain number of vCPUs, and it can also be adjusted throughout the life of the virtual machine. So you can adjust it, for example, in the virtual machine manager. When enough CPUs for all guests, then the VMM can allocate dedicated CPUs. Each guest must like a native operating system managing its CPUs. What if there is usually not enough CPUs? Then there is CPU overcommitment. So overcommitment, providing resources to guests that exceeds available physical resources. So VMM can use standard scheduling algorithms to put threads on CPUs and then some add fairness aspect. So cycle stealing by VMM and oversubscription of CPUs means guests don't get CPU cycles they expect. So consider time sharing scheduler in a guest trying to schedule 100 milliseconds time slices. So therefore, each may take 100 milliseconds, 1 second or longer. So the problem with this is poor response times for users of guest and time of day clocks are incorrect. And then some VMMs provide application to run in each guest to fix time of day and provide other integration features. So next component is we have the memory management. So it also suffers actually from oversubscription. So requires extra management efficiency from the VMM. For example, the VMware ESX guests have a configured amount of physical memory, then ESX uses three methods of memory management, such as double paging, in which the guest page table indicates a page is in a physical frame, but the VMM moves some of those pages to backing store. Another one is install a pseudo device driver in each guest. It looks like a device driver to the guest kernel, but really just adds kernel mode code to the guest. So that is why it is called pseudo device driver. Pseudo means fake. And then we have Balloon Memory Manager communicates with VMM. It is told to allocate or deallocate memory to decrease or increase physical memory use of guests causing guest OS to free or have more memory available. So that's why it's called a balloon, because it can decrease or increase the physical memory use of the guest. And then deduplication is removing of duplication of data or information. So by the VMM, determining if same page loaded more than once, memory mapping the same page into multiple guests. So another component of the OS in VM is we have the I/O. So easier for VMMs to integrate with guests because I/O has lots of variation, already somewhat segregated or flexible via device drivers, and then the VMM can provide new devices and device drivers. But overall, I/O is complicated for VMMs. So why? So many short paths for I/O in standard OSs for improved performance. Less hypervisor needs to do for the I/O for guests, the better. And then possibilities include direct device access, DMA pass-through, and direct interrupt delivery. Again, hardware support are needed for this complications. And then networking also complex as VMM and guest all need network access. So VMM can bridge guest to network, so allowing direct access. So that's why the term is bridge. So that if the guest OS wants to connect to the internet, so it needs a bridge for the guest to connect to the network and or provide network address translation or NAT. So what is NAT? This is a NAT address local to machine on which guest is running. Then the VMM provides address translation to guest to hide its address. So another component is the storage management. So both boot disk and general data access need be provided by VMM. Need to support potentially dozens of guests per VMM, so standard disk partitioning is not sufficient. For type 1, storage guest root disks and config information within file system provided by VMM as a disk image. And then for type 2, store as files in file system provided by the host OS. But for VMM, the VMM is the one who will provide a space for that guest operating system, and it will also decide the minimum capacity at least for that guest operating system to work. Then next is we have duplicate file or create a new guest and then move file to another system. We have move guest. We have the physical to virtual, so P2V, convert native disk blocks into VMM format. Another is we have the virtual to physical, V2P, convert from virtual format to native or disk format. So VMM also needs to provide access to network attached storage, just as networking and other disk images, disk partitions, disk, and others. So another component is we have the live migration. So live migration is the movement of a running guest between two separate physical hosts. So taking advantage of VMM features lead to new functionality not found on general operating systems such as live migration. So running guest can be moved between systems without interrupting user access to the guest or its apps. So it's very useful for resource management, maintenance, and downtime windows and others. So the source VMM establishes a connection with the target VMM. Then the target creates a new guest by creating a new vCPU and others. And then the source sends all read-only guest memory pages to the target. The source sends all read-write pages to the target, making them as clean. And then the source repeats step 4, as during that step, some pages were probably modified by the guest and are now dirty. So dirty means it's modified. When cycles of steps 4 and 5 become very short, source VMM freezes guests, sends vCPU's final state, sends other state details, sends final dirty pages, and tells target to start running the guest. So once target acknowledges that guest is running, the source terminates the guest. So this is an illustration of the live migration of guests between servers. So we have the VMM source and the VMM target. So step 0, so the running guest source or the guest operating system is running in this virtual machine. So first establish the connection between VMM source and VMM target. So that's the first step. And then next is to create the guest target. And then number 3, send the what? The read-only pages. And then step 4 is send the read-write pages. And then number 5, send dirty pages repeatedly. And then after step number 5, then after creating the guest target is running the guest target. And then the guest target is already running, then you have to terminate the guest source because it is already transferred from the VMM target. So examples of virtual machines, we have the VMware. So VMware Workstation runs on x86, provides VMM for guests, runs as application on the other native installed host operating system. This is an example. Aside from Oracle VirtualBox, VMware is also type 2 hypervisor. Lots of guests possible, including Windows, Linux, and others, all runnable concurrently as resources allow. As I've said, if your computer system can allow running 2 or more guest operating systems. And then virtualization layer abstracts underlying hardware, providing guest with its own virtual CPUs, memory, disk drives, network interfaces, and others. And then physical disk can be provided to guests or virtual physical disk, just files within host file system. So this is an illustration of the VMware workstation architecture. So for the hardware, of course, we have the CPU, memory, and the I/O devices. And then for VMware, as an example, the host operating system is the Linux. And then this application is application running natively on the host operating system. And then it has a virtualization layer. So we have 3 virtual machines installed. We have the FreeBSD, Windows NT, and Windows XP from shown in the example. And then they have their own set of CPU, memory, and devices. And of course, applications can run inside the guest operating system. Okay, another one is we have the Java Virtual Machine. Example of programming environment virtualization. It is a very popular language application environment invented by Sun Microsystems in 1995. So it has this notion, write once, run anywhere. So it's JVM is very portable. Includes language specification, which of course it uses Java, API library, and then the Java Virtual Machine or the JVM. Then Java objects specified by class construct. Java program is one or more objects. So because Java is an object-oriented programming language, and then each Java object compiled into architectural neutral bytecode output with that class in which JVM class loader loads. So bytecode, it is a computer object code resulting from compiling a program in a language such as Java that runs on a virtual machine. And then for the class loader, it is a helper component that loads that class files for execution by the JVM. And then JVM, compiled per architecture, reads bytecode and executes. And it also includes garbage collection to reclaim memory no longer in use. And then JVM is made faster by the just-in-time or JIT compiler that turns bytecodes into native code and catches them. So JIT describes a compiler that converts bytecode to native CPU instructions the first time the bytecode is interpreted to speed the later execution. So this is an illustration of the Java virtual machine. So we have the Java program class and the Java API.class files. So the class loader loads the compiled .class files from both the Java program and the Java API for execution by the Java interpreter. So this we have the Java interpreter here. And then after a class is loaded, so this one, the class is loaded, the verifier checks that the .class file is valid Java bytecode and that it does not overflow or underflow the stack. It also ensures that the bytecode does not perform pointer arithmetic which could provide illegal memory access. If the class passes verification, it is run by the Java interpreter. So there is a verification here in the class loader. The JVM also automatically manages memory by performing garbage collection. So also, virtual machines are used for virtualization research. So very popular technology with active research driven by such uses, which is the server consolidation. So unikernels built on library operating systems. So unikernels specialized machine images that contain both an operating system and applications for efficient execution and increased security. And the definition for the library operating systems, the applications that run unikernels containing both the kernel and the application code. So what is the aim of unikernels? This is to improve efficiency and security. We have specialized machine images using one address space, shrinking attack surface and resource footprint of deployed applications. And then in essence, it compiles application, libraries are called, and used kernel services into single binary that runs in a virtual environment. So better control of processes available via projects like Quest V. So Quest V is an example of a partitioning hypervisor. So real-time execution and fault tolerance via virtualization instructions, partitioning hypervisors partition physical resources among guests, fully committing all resources rather than overcommitting. For example, a Linux system that lacks real-time capabilities for safety and security critical tasks can be extended with a lightweight real-time OS running in its own VM. So separation hypervisors like Quest V, each task runs in a virtual machine. So hypervisor initializes system and start tasks but not involved in continuing operation. Each VM has its own resources the task manages. Tasks can be real-time and more secure. So other examples are the Stratum, Siemens Jailhouse, can build chip-level distributed system, secure shared memory channels implemented via extended page tables for inter-task communication, and project targets include robotics, self-driving cars, and Internet of Things. So that is the goal now of virtualization. So robotics, all about self-driving cars and IoTs. So, we're already finished with chapter 18. So, you already know the technical details, the types of virtual machines, all about the concepts of virtual machines. So, if you do have any questions, so please feel free to comment below. So, after this lesson, I will have a demonstration of an actual virtual machine manager, specifically the Oracle VirtualBox. And it is already has an installed guest operating system for you to see how does a typical VMM runs and functions. Okay, again, thank you very much for watching this lecture. I hope that you've learned something, and please don't forget to subscribe to my YouTube channel. So thank you very much. Good day and stay safe.